Alright, welcome back guys. We're going to be looking at section 9.2, and to motivate this discussion I've come up with a couple functions here. So we've got f of x is equal to 2x plus 1, so it's a linear function. We've got this other function g of x. It's x minus 1 over 2. It's actually a linear function as well. It's like 1/2 x minus 1/2. So these are both linear functions. And I went ahead and picked some inputs for our function f. So I just arbitrarily chose these values. So when x is 0, if you plug that in, you're going to get 1 for y. Whenever x is 1, you're going to get 3 for y. When x is 2, 2 times 2 is 4, plus 1 is 5. And then finally, when x is 3, you're going to get 7 for y. Okay, so I can express these as ordered pairs if I want. And 3, 7. Okay, so we've got our x's and we've got our y's. Now what I'm going to do for this second function is I'm going to plug some numbers in for it, x and y, but I'm going to let the x's, or my inputs, be the numbers that I got from my outputs from this function. Okay, so 1, 3, 5, and 7. Okay, and we're going to see what these outputs are. So if we plug in 1, we're going to get 1 minus 1 is 0, and 0 divided by 2 is 0. And then if I plug 3 in, 3 minus 1 is 2, and 2 divided by 2 is 1. And then we'll plug in 5. 5 minus 1 is 4, and 4 divided by 2 is 2. And then finally we plug in 7. 7 minus 1 is 6, and 6 divided by 2 is 3. Okay, so now I'm going to express these as ordered pairs as well. And so hopefully you're noticing something. Hopefully you've noticed that these ordered pairs are just the opposite of these ordered pairs over here. Okay? In other words, the outputs of f are the inputs of g, and the outputs of g are the old inputs of f. Okay? So these are two functions that are examples of inverse functions. In other words, whatever f does to a number, like if it transforms 1 into 3, then when you plug 3 into g, it transforms it right back into 1. Okay? So that's the characteristic of two inverse functions. Whatever one does, the second, or the inverse of that function, will undo it, or do just the opposite. Okay? And so that's what we're going to study today. And the motivation behind this is that in sections 9.3 and 9.4, we're going to be studying two types of functions that we haven't seen yet that happen to be inverses. Okay? Another way to look at this, guys, is the x's in one function become the y's in another function. Or the y's in one function that correspond to one function become the x's, or the inputs, of another function. Okay? Alright, well let's take a look at example 1. So it says, find the inverse of the following relation. So this is similar to what we did over here. Okay? If f is my original function, then g is my inverse. Okay? And so here, if we have this relation, it just consists of these four ordered pairs, and we want to find the inverse of that. Well, the x's and the y's are just going to trade roles, essentially. The inputs of h will become the outputs of h inverse. Alright, so this is how you denote the inverse of a relation or a function. You use this little -1. It looks like it's an exponent, but it's not. It's used to denote the inverse of h. We actually have this key in our calculator. You may have noticed it before. It's this key right here. That doesn't mean x to the negative first power. That means x inverse, the inverse of x. Okay. But anyway, all right, well, the inverse of h will be another set of 4 ordered pairs, except the x's and y's will be reversed. So the pair 5, negative 8, the pair negative 2, 4, and the ordered pair 1, negative 7, and then finally ordered pair 6.2, 3.8. Okay, so this is the inverse relation of h. Now, what would happen if we were to graph these points, or these points up here from these two inverse functions? Well, it would look similar to what we have here. These 3 points that are already graphed for us. So let's say we've got some relation or function g. Then the inverse of g will just be these same 3 ordered pairs in reverse order. Okay, so instead of 2, 4, we'd have 4, 2. And instead of negative 1, 3, we would have 3, negative 1. So what's happening here, or what's significant about the graph of some function or relation and the graph of its inverse? Well, there's some symmetry. That's what's significant. The symmetry occurs because the x and the y's are trading roles. And the symmetry is actually about this axis right here, about the line y equals x. So if you remember, this is our basic linear function. It goes through the origin. Okay. So all of these points in G just get spun about that axis of symmetry to give us these points of G inverse. We can actually see that, I'll show you this, with these two functions that we started out with. I told you that they were inverses. So let's graph them in Desmos. So the first one is 2x plus 1. So that's what it would look like. The second one is, it was x minus 1 divided by 2. Okay. Now you may be saying, well, I don't see the symmetry. But if I type in that line of symmetry, y equals x, then you can see it. Okay. You can see how this line in red is simply a reflection, or all the points that make up this line in red are simply a reflection about this line in green to give us this line in blue. Okay. So for example, this point right here, well, trying to get it exactly. There we go. This point, 1/2, 2, corresponds to this point down here. I can get it just right. There we go. 2, 1/2. Okay. So we see that symmetry in these two functions, in red and blue. So anyway, what I'm getting at is that when you graph two functions or relations that are symmetric, or excuse me, that are inverses of each other, you will always have symmetry about this line, y equals x. Okay. All right. Well, what if we have a relation in equation form? Okay, so like this one, y is equal to x squared minus 5x. How do we find the inverse of it? Well, we just simply swap the x's and y's. So everywhere you see a y, you put an x, and everywhere you see an x, you put a y. Okay. All right, so the inverse relation in equation form will be x is equal to y squared minus 5y. Okay. And that's it. That's all you have to do there. This is the inverse relation. X and y are related inversely. If you notice, the original is a quadratic function of x, and the inverse is a quadratic function of y. So like if you were to graph both of these, one would be a parabola this way, right side up, and the other one would be a sideways parabola. But they would still exhibit that symmetry. Okay. All right. Okay. So we've talked about this idea of a function or a relation having an inverse. Let's look at this example right here. Or let me ask you this. Is there always a guarantee? So this function right up here at the very beginning, I just made this up, 2x plus 1. Was there a guarantee that it would have an inverse? That there's another function out there that'll do just the opposite? Map all these y's right back to their x's, okay, the way g did? And the answer is no, there's not a guarantee that every function will have an inverse. Okay. So let's look at this example right here. So many times a relation may have an inverse, but that inverse won't actually be a function. Okay, so let's look at this function. We can call it f. Okay. So what does this function do? Well, the inputs are the specific years, and the outputs are the costs, respectively, of a postage stamp in each of those years. Okay, so this relationship here between the domain, the year, and the range, or the cost of a postage stamp, is a function. See, because you have one arrow coming off of each input. Now, again, remember, it doesn't matter that in these 3 years, a postage stamp cost 44 cents. But let's look at the inverse, or the reverse. So if the cost becomes our domain, and the year, the corresponding year, becomes our range, then this is not a function. See, and it's this element right here, because 44 corresponds to 3 different years. Okay, so all of this to say, or to show you, or illustrate to you, that not every function will have an inverse that's also a function. Now it'll have an inverse, but that inverse may not be a function. So that's what we want to talk about now. Okay, so to be guaranteed that some arbitrary function has an inverse that's also a function, that original function has to be what's called a one-to-one function. So think about this. If this 44 right here had only gone to 1 year, this inverse would be a function. But that would have meant that only one of these years could have gone to 44, okay? Or more broadly, that each of these years would have to have a unique cost, okay? You couldn't have these 3 years going to 44 cents. And that's what we mean by one-to-one. Each x can only have a unique y, okay? Only when a function is one-to-one will its inverse also be a function. Okay, so think about this. We've got to ensure that each x can correspond only one unique y. And to guarantee that an inverse relation is also a function, each y can only correspond to one x. And having this property is called one-to-oneness. Okay. Now, there's actually an easy way to test for this. It's very similar to the way that you graphically or visually determine whether a relation is a function or not. Do you remember the vertical line test? With that vertical line test, that ensured that each x went to only one y. Well, if you use what's called a horizontal line test, that will ensure that each y corresponds to just one x. Okay, And that's how you check to see whether a function is one-to-one. So if it's possible for a horizontal line to intersect the graph of a function more than once, then the function is not one-to-one, and its inverse will not be a function. Okay. So let's look at some examples here. Actually, this may be a good stopping point for part 1 video. So for the following functions, determine whether they are one-to-one. Okay, so look at A. A is just this linear function, 4 minus x, or negative x plus 4, however you want to think about it. So here's its graph. Okay, well, would it pass a horizontal line test? Well, the answer is yes, because anywhere you put a horizontal line, it will intersect in only one place. So that means that to each x there corresponds a unique y, and conversely or similarly, that also means that to each y there corresponds a unique x. Okay, and so that means the inverse of this function f, whatever it is, will also be a function. Okay, and so this is one-to-one. Okay, f is a one-to-one function. Lots of times you'll see people express it like this. Okay, one-to-one. Now let's look at b. So b is a function, we know it as a quadratic function, right? Because it passed the vertical line test, but it will not pass the horizontal line test. Okay, really anywhere except for this vertex right here. That would be the only place that it would pass the horizontal line test. So because it doesn't pass the horizontal line test, it's not a one-to-one function. Okay, which just means that it has an inverse relation, but that relation wouldn't be a function. Okay, and the reason is right here. Think about these 2 points. Negative 2. Actually, let me draw this using arrows as a mapping, the way we've seen it before. Negative 2 goes to 4, and positive 2 also goes to 4. But if we're going in the reverse order, then that would have 4 going to 2 different values. Okay, and so that's why the inverse wouldn't be a function, because 4 is corresponding to 2 different outputs. And so typically what happens here is with a function like b, you restrict its domain. So instead of considering the entire parabola, you consider only half of it. And if we consider only half of it, then that half will have an inverse that's a function. So anyway, okay, what about part C? This is actually a cubic function, the cube root of x plus 2 plus 3. Well, this will pass the horizontal line test. Anywhere you put a horizontal line, it'll intersect this function at only one point. So this is a one-to-one function. And so it'll have an inverse. And because the original function is a cube root function, its inverse will be a cubic function. And then part D is a 5th degree polynomial. And because we know these polynomials can zigzag back and forth, up and down like a roller coaster, this one will not pass the horizontal line test. So it is not one-to-one. Okay. Alright, well this is a good stopping place. What we're going to do next, guys, is if a function is one-to-one, we want to find its inverse. Okay, similar to the way I did way up here at the very beginning. Okay, I made up f, and then in my head I figured out what its inverse would be. I already knew it was a one-to-one function, because it's just a line, right? So it was one-to-one, so I knew it had an inverse. And we'll talk about how I thought about this to figure out what its inverse would be in the part 2 video. Okay. Alright, so that's where we're going to stop this part 1.